Pregnant father. ora. Sì. Ah.
Hello and good evening. So I'll just share my screen. Hope my voice is audible. Can you tell if my screen is visible now, please?
Sir, it's visible.
Okay, so I'll just start. Okay, so till the last class, in the last two classes, probably we were seeing about the thermal modeling of power electronic converters, right? So that is from a device perspective. How do we model power devices, right? And if we have kind of a heat sink arrangement, then how do we model the thermal chain and estimate what is the device junction temperature, right? So for a given operating condition, we kind of saw how to calculate what is the junction temperature, right? So we modeled the equivalent thermal resistances and we drew the thermal chain, right? And if we know what is the loss in each device, from that we can kind of extract what is the junction temperature. Okay, so this helps us design efficient heat sinks for thermal dissipation. Okay, so today in today's session we will be seeing about a different topic on what are known as bootstrap gate drivers. Okay, so in the industry, bootstrap gate drivers are very widely adopted, all right, and we will see why and how. Okay, and it's a very cost efficient solution. Okay, so that's why it's heavily adopted by the industry and it's very robust as well. Okay, so we'll see about bootstrap gate drivers and their design. By the way, bootstrap gate drivers have been covered so far or no? Can you just tell any coverage about bootstrap gate drivers?
Are you asking in the sessions about the Mount Mitadas
Yeah,
sessions?
yeah, yeah, yeah.
Oh, sir, actually, last 2 weeks I didn't attend the sessions.
Okay, no worries. I think it was more about simulations, okay, simulation software.
Yes, yes,
So I
PCP
cannot
design
be,
and PCP.
yeah. Yeah. So actually, I may not be, I mean, it's not good to discuss questions only on that because they will be mostly theoretical and you can answer them if you just go through the lectures, okay? So that's why I thought of discussing something else so that you also learn something. So we will see about bootstrap drivers, all right? And it's very widely adopted by the industry, okay? So we will see why and how. All right. So, right. So, one thing that you would have realized by now is that probably my screen is opposite. I'm not sure. Oh, yeah, my screen was opposite. Okay. So, one thing that we would have all realized by now is that if you have a half bridge, all right, if you have a half bridge and which means you have two devices stacked across a common DC bus, right? Something like you have a DC bus over here. Let's call this as VDC. All right. So then let's say you have two IGBTs or two MOSFETs. Okay. So, and let us also mark the ground over here. Okay. So this is the power ground. Okay. The reference or the, let's term this as power ground. Okay. So I will denote power ground as something like this. Okay. And you obviously know that, let's say this is kind of a buck converter or whatever it is, buck or boost converter. So you will know that this is the switching node. Okay. So let me call this as SW, okay, switching node. All right. So, so we tell that we give complementary pulses to both the devices. Okay. Right. And you know that for the top device, this is VGS. Let's call this as VGS1, and this is going to be VGS2. Okay. And since we are having complementary device, complementary switching, we are going to get something like this, right? This will be the pulses. Okay. So now can you tell, obviously, the pulses need to be complementary. Why should the pulses be complementary? What will happen if the pulses are same for both S1 and S2?
Cannot switch at same time.
Yeah, so then what would happen is there is going to be a short across the DC bus and there will be a huge current, right? The device will blow up. Okay. Okay. So then that is why we go for complementary switching. But one thing we need to understand is that, okay, you are giving complementary switching, but the point is VGS2, right? Over here, the gate pulse for S2. So what is the reference for gate pulse of S2? What is the reference point? With respect to what are you giving the gate pulse? You are always giving the gate pulse with respect to the source, right? That is why we call this as gate source voltage. Okay, calling it just as gate voltage is incorrect. We have to call it as gate source voltage. With respect to the source, we give positive or zero. I mean, based on that, the device turns on or turns off. Okay. So the point is, as far as S2 is concerned, all right, as far as S2 is concerned, you know that VGS2 means it is referred with respect to, over here you can understand it is with respect to the power ground, right? The source of S2 is equal to power ground, correct? So what is VGS1 referred to? So the reference for VGS1 will be what? It will be the source of S1. So what is the source of S1 over here? So what is this point? Right? VGS1 is with respect to this point, correct? As I think you can see my pen, right? That is a switching node. Okay. So VGS1 is kind of referred to your switching node, right? Okay. Now the point is these pulses will be mostly obtained from a microcontroller. Okay, they will be obtained from a microcontroller. So let me kind of erase these because you know that these inductors are anyway there. So I will not use this space for that. So let me draw over here. This is your buck converter. Okay, fine. So now the point is these pulses are obtained from a microcontroller. Okay, so how do we get, as far as VGS2 is concerned, right? The power ground is a fixed potential. Okay, the power ground is at a fixed potential. So if this is 400 volt, then this point is zero. Correct? That is the idea. Power ground is with respect to a very fixed potential. Okay, so power ground means you can call it as reference to zero voltage. But what will be the reference for switching node? Switching node itself is, that's why it's called switching node, right? It's kind of switching between VDC and zero, VDC and zero, VDC and zero, right? So switching node itself is actually bouncing, correct? Between zero to VDC, zero to VDC and so on. Okay. So you understand the gate pulse for S1, right? When we tell that VGS1 is more than V threshold or whatever it is, right? So it is with respect to the switching node that we are talking, right? And the switching node itself is varying. Okay. So in that case, right? Your switching node itself is varying. So switching node can be either 400 or 0. I mean, either your VDC or 0. That is the idea. So in that case, can we directly give from a microcontroller? Is it possible to directly give from microcontroller? Hello? Are you there? Like, are you understanding what I'm telling? Like, is it possible to directly give from microcontroller? Okay, no worries. So, the point is that what generally people do is in order to give this VGS1, right, they have an isolation stage. Okay, so what people generally do in research labs, right, that is, so let's say you have the microcontroller over here. Okay, I write this as microcontroller. So you will be getting two pulses, right? With respect to what? With respect to your analog ground or your microcontroller ground. Okay, so this is your microcontroller ground. Right, so you'll be getting two pulses. So one can be for the top device and one is for the bottom device. So you can generate two pulses from your microcontroller, right? Okay, and then what people do is instead of directly giving to the gate, instead of directly giving to the devices, what they have is basically an isolation stage. Okay, so they will be having an isolation stage over here. So there will be an isolator and again there will be an isolator. Okay, so what the isolator does is, right, so it kind of breaks your ground. Okay, it makes the potential different. Okay, so for instance, right, so this is how an isolator is represented. Okay, on one side you are having the microcontroller ground, right, and on other side of the isolator you will be having the ground which you want. Okay, so on the other side you will be having the power ground for the bottom, and for the top you will be having your switching node, or let me write it as SW. All right. Oh, okay. So you are getting two signals, right? And we told that it will generate a signal with respect to the analog ground. We call this as analog ground or signal ground. We get two signals with respect to the analog ground, and then what we do is we kind of feed it to an isolator. There are isolator ICs available in the market. Okay, so we will feed it to an isolator. Okay, And as I was talking about isolators, right? So it kind of changes the ground. Okay. So if you give logic high with respect to the analog ground, it can give you a logic high with respect to the other ground that you want. Okay. So on one side, you are having the analog ground. And on the other side, you will have the ground which you want. Okay. So for the bottom device, it is with respect to the power ground. Okay. This is your power ground. And for the top device, it is with respect to the switching node. Okay. So you were feeding pulses something like this with respect to the analog ground, then you will get logic high when the pulse is high. Okay, so when the pulse kind of goes high, you will get a logic high output. And when the pulse goes low, you will get a logic low output and so on. And same over here. You will get logic high and logic low outputs respectively. Okay. Okay. Right. So once we have converted the ground levels, right? So once we have converted the ground levels, they will give to the gate driver IC. Okay. So then it is fed to a gate driver IC. So this is what goes as the pulse to top device VG1, and this is the pulse for bottom device, which is VG2. Okay. So this is the setup. Okay, so you have the microcontroller. Microcontroller is with respect to analog ground. And then what people have is they have an isolator. Because as we just saw earlier, we cannot have the same ground for VGS1 and VGS2. The ground for VGS1 and VGS2 are kind of different. Okay, so that is why we have an isolator. So all of these are IC based. Okay, this is also IC and this is also IC. Okay, again, this is a gate driver IC. Okay, again a gate driver IC. Right. So after the isolation stage, you will feed it to a gate driver IC, and then this is what goes as VG1 and VG2. Right. So this was for the top, and this is for the bottom. So till this point, is it fine? Like, are you able to follow why we need isolation and how this isolation works?
Yes, sir.
Okay. So now the point is this isolation, just for the sake of your information, right? So this isolation can be achieved by three ways. Mostly it's achieved by 3 or 4 ways. Okay, I'll just list it down, but how it works is beyond the scope of this course. So one can be transformer based isolation, which we are very familiar with, right? So transformer based isolation. Okay, so you have something like this. Okay, so you match with the dot polarities, and obviously you understand that over here the ground is different, right? So over here it can be analog ground, and over here it can be power ground. The ground is different because it works only by mutual coupling, right? It doesn't care about the electrical connection as such. So one is transformer based, or which is kind of based on the magnetic field, right? Transformer based is kind of based on magnetic field. So the obvious dual of that is going to be based on electric field, right? Or capacitive isolation. Capacitive isolation. So in the forward path, they will realize a capacitance, and in the return path, they will realize a capacitance. And you know that both the plates are kind of separated by a dielectric, right? So it is not direct connection, right? There is an isolation over here. Okay. So one is transformer based, the other one is capacitor based, and you also have optocoupler based isolation. Okay. Optocoupler based. So optocoupler means like you would have studied about photodiodes, right? So diodes that turn on in the presence of light. Okay, when you give a light excitation, then the BJT will get triggered. Okay, so that is the idea. So you have a BJT. Okay, so you will have a BJT, and we generally tell that it has to have a base current such that VBE is more than 0.7 volt. So what people do is they will make photons to fall on the base of the BJT. Okay, and that is how the BJT gets triggered, right? So what people do is if there is a logic high signal, right? So they will convert it into light energy, right? It's very fast, right? The speed is very high. So what they do is if there is a logic high signal, it gets converted into photons, and they make the photons fall on the BJT, which is in the other side of the isolation. So since the triggering is happening with light, not during direct electrical connection, it provides the isolation. Okay, you can read more about it. Okay, this is very widely used nowadays. Very widely used. Optocoupler based isolation, even capacitive based isolation is very widely used. Transformer based isolation is very slow. Okay, that is why people don't use it. But optocoupler based is because it is based on light, it is very fast. Okay, the isolation time is also very low. Okay, so if you read the data sheet of ICs, right, they will give you what is the delay. Okay, so for example, let's say you take a NOT gate. Okay, you take a NOT gate. So you know that NOT gate kind of converts your logic high into logic low and vice versa, right? What does a NOT gate do? It will convert logic high to logic low and logic low to logic high. So A becomes A bar, right? So if I give a t equal to 0, right? What I ideally expect is output should be something like this, right? But practically you will see that there is a time delay. Okay. So there will be a time delay, which means that you're going to get something like this. So this is called as a propagation delay. Okay. It happens due to the IC. Okay. This is the delay in the IC. So the point is with isolators, right? With isolators, if you have transformer based isolation, this delay will be larger. Okay. That is why people go for optocoupler based isolation because it is based on light. Okay, and light travels at 3 into 10 power 8 meters per second, which means very, very fast. Okay, so the delay will be in the order of a few nanoseconds, right? Okay, so this is one way, that is optocoupler based isolation. And people have what are known as semiconductor based isolation. Okay, I'm not going into that, just for your info. Okay, so these are the different ways by which you achieve isolation, right? So kind of we have isolated the microcontroller from the power side. Okay, we know that anyway in the power side we have to provide isolation for the top because obviously VGS1 is with respect to the switching node. Okay, whereas VGS2 with respect to the ground. So we have to convert the logic high and logic low accordingly, whether it is with respect to the switching node or whether it is with respect to the power ground. Okay, so that is the purpose of this isolation stage. And then we will have the gate driver. Okay, fine. So the point is you see, observe over here, you are having mainly two gate drivers, right? That is one gate driver just for the for driving the top side device, one gate driver just for driving the bottom side device. Okay, so you're having two gate drivers, and this kind of is a cost concern. Okay, for the industry to adopt Industry wants very cheap solutions. They don't want to have these costly solutions where you have two isolator ACs and then two gate drivers and all. Okay. Their idea is that they don't care about whether you have isolation or not. They only care about how cheap you can make the solution. Okay. If you are able to avoid direct switching of S1 and S2, right? If you are able to avoid direct switching of S1 and S2, if you can achieve complementary switching of S1 and S2, it's fine. Okay. Okay. So till this point, any doubt? Any clarifications?
No, sir.
Okay. So now the point is in this figure, right? In this figure, can you tell if any stage is not necessary, that is extra? The gate driver is obviously required, right? Gate driver is required. Now, can you tell, can I do away with this isolator or this isolator, right? If so, what will happen if both these are common, right? Can I do that? Obviously, this ground and the switching node cannot be shorted, right? Because switching node is actually changing from 0 to VDC, 0 to VDC continuously. So this isolator is kind of must. Okay, in this kind of an arrangement, this isolator is a must. Okay, because I cannot have my microcontroller ground same as switching node. Okay, these two cannot be matched. But this is also a fixed reference, right? That is, the power ground is fixed at 0, right? This is a fixed reference. And this analog ground is also a fixed reference, right? So then this isolator is kind of not required, okay? Without this also, you can design gate drivers, okay? This isolator is kind of not compulsory, okay? This is compulsory, and the gate driver IC is compulsory, but the isolation for the bottom device is not compulsory. Okay, fine. But nonetheless, you see that you are having multiple ICs over here, and that is kind of a cost concern, right? So that is where bootstrap gate drivers come into play. This is conventional gate driving, okay, without bootstrap. Okay, fine. So we were talking about, we were telling that from isolator, it will go to the gate driver IC, right? But you would have studied that what is actually there inside a gate driver IC is kind of a CMOS arrangement. CMOS is complementary MOS arrangement, right? That is, you will have an NMOS over here and then a PMOS over here, right? So this will be VDD, this will be VEE, all right? So the idea is that, and yeah, and then from here you will take the gate connection output, you will give it to RG, right? And then it goes and connects to the power device. Okay, and the return path will be something like, okay, fine. So are you able to understand this till this point? So what will happen when you give a positive pulse, right? So when this device turns on, that is when this device is on, the path will be something like, we will trace the path, okay? So then I think it will make things clearer. All right. So the path will be something like, it comes from VDD, it goes towards RG, right? And then there will be CGS capacitance. So it goes through CGS and then back. Okay. So when you give a positive pulse, right? When you give positive pulse, this device turns on, right? So VDD comes over here. So the equivalent path is something like this. Okay. And when you give a negative pulse, this device turns off, this device turns on. So that is why the paths will be completed within this loop, within the bottom loop. Okay. Fine. So this is just a CMOS arrangement. Okay. Just allow me a second. I will just start. Okay. Yeah, sorry for the disturbance. I'll just continue. Okay. So we were talking about the structure of the gate driver, right? So we just told that, yeah. So you have kind of a CMOS arrangement. Okay. So this is a CMOS arrangement, right? So this you can understand this is an N channel MOSFET. This is a P channel MOSFET or PMOS. Okay. So, okay, I'm sorry. Just a second. Yeah. So the arrangement is something like, so the arrangement would be, you have something like this, okay, and then you have something like this, So you have something like this, right? And then from here you take out the gate connection. Okay, fine. So this is your VDD. We told that this will be your VEE. Okay, this is RG, and this is connected to the device. Okay, so what you will be having is, we studied about decoupling capacitors in earlier lectures, right? So you'll be having decoupling capacitors with respect to the source. Okay, so if let's say this is a switching, so this can be either the power ground or the switching node. So based on this, the capacitors will be from VDD to the ground or VDD to the source of the device. Okay, so this can be either this or switching node. Similarly, from VEE as well, you'll be having something like this. Okay, fine. So as you can understand, the path would be something like, when this device turns on, right? When this is on, then what would happen is the path would be something like this. So VDD kind of comes over here, then it goes through RG, okay? Goes through RG, goes through the capacitance, right? And then to the source. This is the path for current, right? And you can ask how it would return, right? So how would it return? Now we have reached the ground, right? So the ground is same over here. So it will go back through the capacitance. So can you understand the path? That is, let me name this as, let me give names, okay? Let me name this as QA and this is QB, okay? So what would happen is, when QA turns on, right? When QA turns VDD, it will go through QA, right? Then goes through RG, goes through CGS of the device, and then you have reached the ground, that is the source potential. So we told that source potential can be either the switching node, right? Either the switching node or the power ground. Okay. So now that we have reached the power ground, that is this point, right? That is the other side of the capacitor. So it will complete its path through the capacitor, right? So it will complete its path through the capacitor. Can you understand this path? Through capacitor, it reaches VDD. This is the path of the gate current. Can you understand this? Both of you, like Anandi and Selvakumar sir? I don't know whether I'm there or not. Okay, I'm there. Can you understand this? That is
Sir, if
when
it is
this device
power
turns
ground,
on. Sorry? Tell.
if it is power ground, it is okay. Is it okay? If it is switching
Uh,
node, how it complete the path?
yeah. See, um, you can understand that if it is switching node, right? If it is switching node, it is going to be either 0
Going to
or
zero.
VDC, right? It can be either 0 or VDC, right? If it is switching node, it will be something like this. Switching node is going to be something like this, correct?
Yes.
So then what happens is, as far as the gate current is concerned, that is, I was telling that we are seeing only VGS, that is gate voltage with respect to the source. Okay. So now the point is, let's assume you're talking about a switching node. Okay. And let's say that we are in this particular interval, that is we are at VDC interval. Okay, that is the switching node voltage is equal to VDC, right? In that case, you can understand that the voltage over here is going to be VDC, right? Now the point is, over here on this side you are having VDD, and on this side you are having VDC, right? Because this capacitor is also connected between VDD to the switching node. Okay, this capacitor is connected between VDD to the switching node. Okay, the capacitor is connected between VDD to switching node. Okay, so as far as the gate current is concerned, right, it will come over here. It comes like this, right? It comes like this over here. It has come over here. It is seeing VDC voltage over here, and it has a direct connection through this capacitor back, because this capacitor is also at VDC. Okay, it doesn't matter whether it's at 0 or whether it is at VDC, because this potential and this potential are going to be same. Do you understand? The potential is same. Okay, that is what the current wants. Sorry? I'm not able to hear.
No, sir.
Are you understanding?
Yes, sir. You're saying
Okay,
that
so
you are connecting that the VDD capacitor you are connected, right?
uh,
That and here the CGS, both are same.
hmm.
No, right.
This
No, right.
no
It
no
is
no no
parasitic.
no. This is decoupling capacitor that we connect externally. Okay, it is not CGS. This is a decoupling capacitor which we will connect externally. Okay, this is something that we connect externally. Right? So you see the current path. So if I have to draw it in a different fashion, right? So let me draw this capacitor directly. Oh, it is not getting erased. No worries. Now the point is, if let's say you want to turn off the device, okay, you want to turn off this device, which means that you don't want to give VDD, you want to give VEE, a negative voltage of -5 volts, or it can be 0 volts, whatever it is. So then what will happen is, you will turn off QA, you will turn on QB. Okay, you will turn on QB. So what happens if QB is turned on? VEE appears at this point, right? QB is turned on, so VEE appears at this point. So the current part would be something like this, through RG, through this capacitor, and back. Now the point is, as I was telling previously, this capacitor is connected between VEE to the switching node. Okay, between VEE to the switching node, right? So now we have reached the switching node, same point, right? So it will come back through this. Do you get this? Okay. So the point is, what is this VDD? This VDD is like, let's say we tell +15 and -5, right? This will be VDD and VE. But what is +15 and -5? +15 and -5 volts with respect to the switching node for the top device. +15 and -5 volts with respect to the power ground for the bottom device. Okay, +15 and -5 volt with respect to switching node for the top device. Okay, and +15 and -5 volt with respect to power ground for the bottom device. Okay, so that is why I'm telling, see, this VE is basically +15 volt or -5 volt with respect to the switching node. Okay, so let's say switching node is 400 volt. Switching node is 400 volt. if you tell that VE is minus 5 volt, right? If you tell VE is minus 5 volt, it is minus 5 with respect to switching node, which means that it is actually at 395 volts. Okay, with respect to the ground, with respect to the power, it's 395 volts. Similarly, this point is at switching node, right? This particular point is at switching node. And this particular point is at what? VE with respect to the switching node. So the voltage across this capacitance is going to be what? This will be with respect to the switching node, and this is also with respect to switching node. So this effect of switching node kind of gets cancelled. So you will be getting proper minus 5 volt with respect. Do you get this? Like both of these voltages are with respect to the switching node. That is why the current is finding a path back. Okay, current needs only potential to flow. Okay, it doesn't care about what is the absolute value of the voltage, right? So here also it is with respect to the switching node. It is all here also it is with respect to the switching node. Okay. So instead of these NMOS and PMOS, people also use BJTs, NPN and PNP BJTs. Okay, something like this. Right? Something like this. People also use this. Okay, so this is what is actually there inside a gate driver IC. Okay, if you open up a gate driver IC, this is what you will find. There will be a complementary MOS arrangement. Okay, CMOS arrangement, we call it. Okay. Now coming back to the point, right? So over here inside the gate driver, you will be having something like this. Okay, something like this inside the gate driver. Okay. So what we try to do with this bootstrap gate driver is that the motivation is instead of having two isolators and two gate drivers, right? Instead of having two isolators, can I use some arrangement, right? Can I use some arrangement which will allow me to drive both S1 and S2? Okay, I want to drive both S1 and S2. Over here, you see for the top, there is a separate isolator, gate driver, and so on. For the bottom, there is separate isolator, gate driver, and the gate circuit. The motivation for Bootstrap is can I have an arrangement through which I can drive both S1 and S2? Okay, do you get the motivation? Like that is why Bootstrap gate drivers came into play. That is, can I do away with this circuit and have an arrangement which will allow me to drive both S1 and S2? Okay, fine. So, okay. So the idea is that I want to have a single source. Okay. So over here, what you are seeing is, right? Over here, what you are seeing is, since there are two gate drivers, you will have separate VDD, separate VEE for the top, separate VDD, and separate VEE for the bottom. Right? For the top side, you will have separate VDD and VE with respect to the switching node. For the bottom side, you will have a separate VDD and VE with respect to the ground. Okay, only then you can get plus 15 and minus 5, right? For the top side and bottom side separately. Okay, so the idea is, can I have only a single supply which will allow me to drive both S1 and S2? I want to have only single VDD, but I want to be able to drive both S1 and S2. Do you get the motivation?
Yes.
Okay. So now the point is, if you want to get this VDD and VE, right, getting this VDD and VE is not a simple affair. It's kind of a costly affair. Okay. So there are ICs which will, you would have learned what are linear dropout regulators, right? Using Zener diodes, they try to achieve precise voltages and all. So these are basically costly and they also occupy a lot of space. Okay. So the idea is I don't want to use multiple supplies. I don't want to have multiple VDD, multiple VEs just to drive top and bottom. Okay. With a single supply, I want to drive both top and bottom. Okay. So with that as a motivation, people came up with this particular circuit. Okay. Bootstrap circuit. Right. So first I will draw the circuit and then we will slowly evolve, right? And we will also see what are the drawbacks of the circuit as we go along. Okay. So let's say you are having VDD over here, right? You are having VDD, which is your plus 15 volts, right? Gate drive supply plus 15 volts over here, right? Fine. So what I will have is right. So what I will have is first I will right. I will just erase and I will redraw in a better fashion. Okay. Okay. So let's say I have VDD over here, right? And then for the bottom device, right? For the bottom device, I will be having for the bottom device, I will be having the CMOS arrangement. I am drawing the CMOS arrangement with these kind of switches. Okay. Generic switches. And from here, you can understand that you will give to the RG for the bottom device. Let me call it as RG2, right? RG2, and then you will give it to the power side. Okay. So let me call this as this device is S2. Okay. And let's call this as Q3. Let's call this as Q4. You know that this is going to be CGS2. So from this, right, I have not yet completed the circuit. But if I want to turn on S2, what will I do? And if I want to turn off S2, what will I do? So from this arrangement, can you guys just tell? I want to turn on S2. So what should I do to turn on S2? Which device needs to be turned on? Q3 or
Lower
Q4?
Q4 lower.
So if I turn on Q4, then what will happen?
Q4 give the path. Q4
So,
RG2 device.
right. So if I do like that, will the device turn on or turn off?
Okay, the
See,
VDD
this
will
is
not be there, so it will be off. It will go to off.
yes, yes. So what you have to do, you have to turn on Q3, right? If you turn on Q3, then the path will be VDD, Q3, RG2, then the device, right? That means the device will turn on.
Yes.
Yes. And if I want to turn off S2, right? If I want to turn off the device, then what I will do is I will turn off Q3 and I will turn on Q4. So then it will be like Q4, RG2 and the device. So from the capacitance, you will take away charges, right? The capacitance will discharge through the gate resistor, right? Simple, right? Just an
Yes.
RC circuit.
Yes.
Okay. So this is for the bottom device. For the bottom device, I think it is very simple, right? But now let's come to the top side, right? So for the top side, what people did was, so can I have some arrangement which will allow me to have a single supply, right? So that was the question. So what people did was, I will have a resistance over here. Okay, so let me not draw this. We will arrive at these. Okay, fine. So I will have something like this, right? And then I will charge up a capacitor. Okay, I will charge up a capacitor. I will name this as C boot. Okay, I will charge up a capacitor. I will name this as C boot, bootstrap capacitance, right? And then I will be having something like this, same arrangement, similar arrangement. Okay, from the middle, let me draw it better. So something like this, and then from the middle, I will take tapping, give it to RG1, right? And then I will feed it to the device. Okay. I will have something like this, right? CGS1, and this is obviously your S1, okay? And we will name this as Q1 and Q2. Okay, so see from the perspective of C boot, okay, you know that capacitance is a voltage shift element, okay? It doesn't allow sudden change in voltage. So assume that C boot is a proper voltage source, okay? Assume C boot is a proper voltage source. If I want to turn on S1, so what will the path be if I want to turn on S1? Through?
Q1.
So yes, so through Q1, then Q1,
RG.
RG1, and then the
CGS
device, right?
to be.
And then the device and back through this particular, back through this particular connection, right? This is your switching node connection. And if I want to turn off S1, what will I do? If I want to turn off S1, I will just turn on Q2, right? If I turn on Q2, then the capacitance will discharge through RG1 and Q2, right? That will be the path. Okay. So now the question is, I have VDD over here, right? I have VDD over here. How do I charge up C boot, right? That is a question, right? How do I charge up C boot? Okay. So you can imagine that. Wait, let me take a new slide. Okay. So right. Hmm. So now the point is, how do we charge up C boot? Okay. So how will I charge up C boot? So what people came up is, when S1 is okay, so let's write the path. Okay, I think it will be easier. So for S1 turned on, okay, S1 during turn on condition, the path is going to be C boot, then Q1, and then RG1 through CGS1, and then back to C boot. Okay, and if S1 needs to be turned off, right, the path is going to be The path is not going to include C boot. It is going to be something like, let's start from CGS1, CGS1, Q2, RG1, and back to CGS1. Do you agree so far with this? Do you agree? Is this fine?
Yes, sir.
Okay. So now the point is, how do I charge up C boot? Okay, C boot is not a voltage source as such, right? It needs to get some voltage. I mean, it has to charge up. Okay. So how do we charge up C boot? Because during S1 turn on condition, right? When S1 is turning on, I need C boot to maintain voltage at plus VDD. Okay, I need C boot to maintain 15 volts. Okay, I need C boot to maintain 15 volts. How do I charge up C boot to 15 volts? That is the question now. All right, how do I charge up C boot to 15 volts? So what people thought was, see, you can observe that when S1 is turning off, right? When S1 is turned off, that time the path does not include C boot, right? The path is only through CGS1, Q2, RG1, CGS1, right? So the path does not include C boot. So what people thought was, I can have, so can you tell like what can be the path for C boot to charge up? Look at the circuit. When S1 is off, right? S1 is off. So when S1 is off, obviously S2 is on. So this is implied. Okay. When S1 is off, S2 is on. Okay. So S2 is on. So can you tell me the path for C boot to charge up? Think from VDD, right? C boot should somehow charge up to VDD. So you start from here and tell me how C boot will charge up. The path, just the path. Okay.
Directly
S1 is
connected to
turned
the plus.
correct. So VDD and then C boot, right? And then what will be the path? So you came over here. You're right, right? So you started from VDD. So you slowly came over here, right? And then from here, where will it go? You are charging up C boot, right? It has to complete the path back to VDD. How will I go back to VDD? You're right. Continue.
It will come Q2 because
It
S2
will
will
come
be
over
off.
here. Then
Q2
S2 is
or
on,
G1.
right? It is a short circuit that will complete the circuit.
then then where will it go? Will it go to Q2 or will it go straight to switching node?
Switching, it's
Correct. Right? It can go directly to switching node, shortest path, right? And then we told that if S1 is turned off, S2 is turned on, right? So the current will flow through S2, right? Through S2 and back to VDD. Are you understanding this path? Right? So what will happen? Slowly, C boot is getting charged up, right? Do you understand?
S1 off, Q2
Huh.
or Q2 will be on.
Q2
In
will
that
be
path,
on, correct?
so
Correct.
it will not be in that path.
So the point is, see, okay. So the point is you came till this point, right? You are over here. Now it is seeing two paths, right?
Yes.
One is through Q2 and one is through switching node, right? So the point is if it goes through Q2, right? It has to circulate over here only. Where is the completion, right? So Q2, RG1, CGS1, back to Q2. I mean, there is no continuation. The other path is Q2, RG1, CGS1, and then it will go to S2. But you can understand that current always prefers the least resistance path, right? One path is direct short circuit, right? I mean there is a direct path from Q2 to switching node. There is a direct path. So obviously current will prefer this particular path, right? Why will it go through the resistance? Why will it go through RG1?
No. My
Do you
question
understand
is
this?
no. My clarification is okay. This path
Hmm.
is okay. My clarification
Hmm.
is during that instant, the QT also will be on to turn off S1.
Correct. Correct.
So that current only will circulate here only, yeah. Q2
So now
RG1
the
and
point is, so when S1 is turning off, right? So S1 is turning off means you're removing charge from CGS1. So CGS1 has to discharge, right? CGS1 has to discharge, which means current should go like this. You're removing charges from CGS1. So the discharging current for CGS1 will be something like this, right? Do you understand? From CGS1, RG1, Q2 back to CGS1.
okay.
That will be discharging current of S1. As far as the charging current of C boot is concerned, right? Charging current of C boot came from VDD, C boot. It came till this point. Now it can either directly go to switching node or it can go through Q2, RG1, CGS1 and then switching node. You tell me which is the least resistance path.
Okay.
I mean, do you understand like what is happening? C boot is getting charged up over here. Current prefers the least resistance path. That's why I'm telling it can directly go to the switching node. All right.
Okay, sir.
No, no. If you have any doubt, you ask. No,
No, no,
it's
no.
not
No,
okay.
no. No. My doubt is
Hmm.
okay. Charging path. Okay, it is taking least distance switching node path. During
Hmm.
that time, this also will flow. So this current,
Hmm.
it will be same directions in the switch,
Correct. Correct.
the charging current. So this
Correct.
current will add up to switching node. No.
So over here,
So, so
so in this
what is
particular line, the current is going to be both. Yes.
yes. So how it will be? It will not affect anything in that place, switch or the bottom
No,
or
right.
top.
It is only because of KCL, right? So just
Okay.
if you apply KCL, this particular current will be equal to the discharging current of S1 and then the charging current of C boot.
Okay.
You got it right?
Okay. Okay.
Okay.
Okay.
Right.
Then any of the device, either S2 or S1, this current together current should be there. For
Correct. It
VDS,
will be there. It
sorry,
will be there.
it will be
Yes,
there.
yes, it will be there.
IDS will be both the current.
Correct. Hmm. So for yes, so you are asking if it is through S2, right? So the device current of S2 is now both. You are right.
Yes. Yes.
So IS2 will be equal to both the load current, whatever is the load current, we don't know, right? Like let's say this is a buck converter, something like this. So there will be load current as well as the charging current of C boot. Okay, so if you are asking this, it is yes, both the charging current of C boot as well as IL. Okay, fine. That is IS2, agreed. Now the point is, you see the charging path of C boot, right? You started from VDD, right? So you started from VDD and then you went to C boot, right? This is C boot. I'm drawing the equivalent circuit. From C boot, you went to switching node and then there is S2, which is turned on, right? I'm drawing a direct path and then back. So do you see any problem in this kind of charging? Can you directly charge up a capacitor across voltage source or is some element required? So C boot is initially uncharged. Okay. C boot is initially uncharged. You are charging up C boot. So do you see any problem if you directly do like this?
We have to connect the resistor before the
Correct.
capacitor.
Correct. Because if you don't have resistor, then what will happen is there will be huge current, right? The impulse current will be very high. So you have to connect a resistor. That is why what people do is they will connect a resistor. Okay. So let us call this as R boot. Okay. So now we have connected a resistor. We call this a current limiting resistor just to limit the current. Okay, or else the charging current will be very high. You cannot have very high current flowing through a circuit. It will, as Selvakumar sir told, it will also affect your IS2 operation. You want this particular component to be low. You don't want this to be very high, right? So you will add a R boot, right? That is a current limiting resistor. Correct. Okay. So now the point is, see,
At the same
again they
time,
will
if
come,
it,
huh?
at the same time, if it is
Hmm.
the limiting resistor also will not be very high. The
Yes,
potential, if it is capacitor potential, if it is exceeds on VDD, it may reverse now. So reverse protection to be given in this place now.
correct. So the point is, you don't, one point is, you see, during S1 turn on condition, right? We told that C boot will go from C boot, Q1, RG1, CGS1, and then back, right? C boot, Q1, RG1, CGS1, and then back, right? Something like this. But you can imagine that C boot, the current over here has two parts. One is through Q1, the other can be backflowing, right? As sir is telling. So it can backflow. You don't want that. So what will you do to prevent backflow?
And connect
What
a
element
diode.
should you add? Yes. So what you will do is you will add a diode. Okay. So apart from the resistor, you will add a diode like this. Okay. So it will allow only charging of C boot. Okay, it will allow only charging up of C boot. I don't want C boot to discharge in this direction. Okay, so now we will write C boot charging up will be C boot charging up will be VDD or boot, which is for current limiting. Then it will go through bootstrap diode or deboot, which is for preventing backflow of current, right? And then it will go through C boot, right? And then from C boot, it will go through switching node through S2, right? Through the channel of S2 and then back to VDD. Do you understand this? Is this fine?
Yes, sir.
Okay. So I think from here, S2 is very simple, right? As far as S2 is concerned, we saw it earlier itself. S2 is like during on condition, VDD, Q3, RG2, then through CGS2 and back to VDD, right? And during off condition, it is even simpler. It is going to be CGS2, Q4, RG2, CGS2. It's very simple as far as S2 is concerned. Only for S1, we saw that we are having an intermediate state. So what we have done, we were having only VDD. But using a capacitor, we have designed or we have derived a supply. We have derived 15-volt supply using capacitor. Okay. Without having to basically isolate between the S1 and S2, we did not have any isolation, right? Without isolation, we were able to get 15 volt. That too with respect to the gate source, right? C boot is with respect to the switching node, whereas VDD is with respect to the power ground, right? Indirectly have got some kind of isolation. VDD is with respect to the power ground, whereas capacitor C boot is with respect to the switching node. Okay. So you have been able to charge up C boot from VDD, right? And C boot is with respect to a totally different potential, right? So that is the beauty of bootstrap gate driving. That is, you're able to kind of use only single gate driver supply just to drive both S1 and S2. Okay. So again, I will just recap. When S1 has to turn on, so the S1 will turn on from C boot through Q1, through RG1, CGS1 and back to C boot. Okay. And if S1 has to turn off, it will be from CGS1, Q2, and then RZ1 back to CGS1. Okay. That is S1 turn off. Now the point is, you understand if S1 is turned off, S2 will be turned on. So what will happen is the C boot will charge up, right? So from VDD, R boot, D boot, C boot, and then and then through S2 and then back to VDD. Okay. This is the path of charging for C boot, and we saw that we have to limit the current through charging for during charging. That is why we added a bootstrap resistance R boot, and we also had to make sure that there is no backflow from C boot, right? That is, there should not be any backflow of current back to VDD. That is why we added a diode, which makes it unidirectional. Okay. So you also understand, if let's say S1 is on for a very long time, okay? S1 is on for very long time. Will it cause any problem?
S1.
So if
Capacitor
S1, huh, capacitor will,
has a fixed value, right? It can give some. It is can provide the current for a particular time. So the value of capacitor should be high.
Left tighter.
just a second. I don't know, I got logged out. Yeah. So if S1 is on for very long time, right? So can you tell what will happen? Is there any problem first of all if S1 is on for very long?
I have to select the capacitor according that
Correct.
means
So what will happen is the capacitor will go on discharging. So the capacitor voltage will go on falling. Okay, the C boot capacitor voltage will go on falling, right? So you have to size up your capacitor accordingly, such that it is able to give that much. It is able to hold up that voltage for that much amount of time. Okay, so C boot selection is actually kind of has to be made properly according to the switching frequency and application. Okay. So for instance, if you are having, let's say 10 kilohertz application, 10 kilohertz means 100 microsecond is your switching period, right? So then your capacitor has to be able to supply 15 volts at least for 100 microseconds continuously without discharging, right? During those 100 microseconds, you don't want the capacitor voltage to fall from 15 volts to let's say 7 volts or 6 volts, right? You want it to maintain it almost constant, right? So the idea is keyboard needs to be selected very properly. Okay. You just give me a second. I will have some water. Okay. Okay, just a second. Yeah. So in this circuit, what we did was we included R boot, and then we also saw that we had to use a diode, right? We called it as D boot. Okay. Okay. Now the point is, we were talking about how to design your C boot, right? How to design the bootstrap capacitance, right? So as we just saw that this C boot kind of discharges when Q1 is on, right? When Q1 is on, the path is going to be from C boot, right, through RG1, through CGS1, and then back to C boot. So as this happens, right, your C boot kind of falls. Okay. So how much can it fall? Your C boot cannot fall too much. Okay. Why can't your C boot fall too much? So what will happen if, let's say, I am at 15 volts, right? And in one case, I am falling from 15 volts to 7 volts. And in the other case, I am falling from 15 volts to, let's say, only 13 volts. So what is the difference between these two cases? Why shouldn't I fall from 15 volts to 7 volt? What will happen? Like that is also 7 volts is also greater than my threshold voltage. The device will continue conducting. So why shouldn't I fall like this?
Capacitor dielectric may got break.
Okay, so the point is, let's say I was at 15 volts initially. I went to 7 volts. Okay, it has fallen from 15 volts to 7 volts. In 100 microseconds, I have fallen from 15 volts to 7 volts. So then what is the problem? Is there any problem on the operation of S1? Will there be any problem on the operation of S1? So your VGS1 was at 15 volt. Your VGS1 became 7 volts. It became 7 volts. Can I operate the device at lower gate source voltage? Why or why not? What will happen if I operate at very low gate source voltage? Think in terms of
There will
RDS
be a
on.
loss.
Yes. So if this happens, then RDS on increases, right? So then there will be conduction loss. Conduction loss will be more. Conduction loss also increases. So you don't want this at any case, right? You want your voltage to fall only from 15 to 13 volts. Anyway, your voltage will fall, right? Because it's a capacitance. Capacitance, when it discharges, it will always fall. But you don't want the fall to be too much, right? That is how you will design your bootstrap capacitance. You don't want the fall to be too much. So if I want to achieve this, what should I do? The capacitance should be high or low if I want to achieve this. Capacitance should be high, obviously, right? So that the discharge is very low, right? The capacitance should be high. Now the point is, if capacitance is high, what about the charging time? The charging time, it should also be high, right? Only then I will be able to charge up the capacitance. It will take more and more time to get charged up, right? It is easier to charge up, like it is easier to charge up 1 nanofarad of capacitance. It is difficult to charge up 100 nanofarad capacitance, right, to the same voltage. 1 nanofarad capacitance will quickly charge up. Okay, so that is the trade-off you need to do. Okay, so how do I size up the capacitor, right? So that is the answer. That is the issue that we are dealing with right now. So how do I do that? Is let me take this to the New slide. Okay. Paste it over here. And then, yeah. So how do I do that? Is see, from the device perspective, if you go to the device data sheet, they will tell you what is the gate charge required, QG. Okay. Gate charge. It is given in the device data sheet. Okay. So from that, so can you link what is the capacitance with charge? So how is capacitance linked to Q? Just in any generic capacitance. How is the capacitance linked to the gate? How is capacitance linked to charge Q? What is the relation between C and Q? How is capacitance related to charge? Q is equal to CV. Have you heard of this? Is this fine? Q is equal to CV.
Yes, sir. Yes.
Okay. So now the point is, from perspective of gate, you know what is QG, right? From data sheet, you can know what is QG, right? And let's say that I want the voltage to fall from 15 volts to 13 volts. Okay. So I know what is delta V. Delta V is my desired fall, right? I don't want the capacitor to discharge more than 2 volts, right? That is, I want it to fall only from 15 to 13, not more than 2 volts. Okay. So this is the design parameter. I don't want the capacitor to fall not more than 2 volts. I don't want it to fall more than 1 volt or something like that. So based on that, you can design what is C boot. Boot will be QG divided by delta V. That is, the C boot has to supply this much amount of gate charge to the device. So if it supplies this much amount of gate charge, if it supplies QG amount of gate charge, how much the voltage can fall, right? That is what defines your C boot. Okay. So obviously, if I don't want C boot to fall too much, I mean, if I don't want the voltage to fall too much, C boot will be more and more. Okay. Do you get this relation? C boot is equal to QG by delta V. Is this fine?
Yes.
Right? Selva Kumar sir, like if you are there, are you able to get this?
Yes, sir.
Okay. So let me take this. So we have designed what is C boot. Okay. So we just need to design what is our D boot. Okay. So the idea is how to size D boot. What is the voltage rating of this D boot? Okay. We have to know what is the voltage rating of this D boot so that I can accordingly buy a bootstrap capacitor. Okay. So we will see the path, right? When C boot is charging up, right? When C boot is charging up, the path was yeah. So when C boot is charging up, the path was VDD, R boot, D boot, then C boot, and then through S2 back to VDD. This was the charging path as indicated in green over here, right? So this is when it is on. So in order to find out what is the voltage rating of the diode, we have to consider when diode is off, right? So when will the diode be off? The diode will be off when S1 is turned on during this particular interval, right? During this particular interval, diode is off. Do you get this? When S1 is on, diode is off, right? That is the C boot is not charging. Okay. So from here, we will write the KVL equation. Okay. So um, Okay. So when the diode is off, right, we have to find out what is the voltage across this diode VD. That will give us how to size up the diode. Okay. So we will just write a KVL equation for that. Okay. Fine. So what do we do for that? So it will be, let's start from VDD, right? We will just write a KVL equation, right? So it will be VDD minus I into R boot, right? Minus VD, right? And then it comes to bootstrap capacitance, which is VC boot, right? We have come to VC boot and then minus V switching node and then back to 0, right? When S2 is on, right? Okay. So this is the path when the S2 is on, okay, and S1 is off. All right. Is this fine? This is the charging path for C boot. Okay. So if we assign some numbers, right? So let's say VD boot is 15 and there will be some drop across the resistors. Let's say it is around 1 volt or something. There will be drop across the diode. Let's say it is 0.7 volts, right? And then you have VC boot, right? And then V switching node is basically the voltage across VS2, right? Again, there will be drop across the device when it is conducting, which is 0. So you will get VC boot is equal to around 12.3 volts or something. Okay, so you understand that the bootstrap capacitor cannot charge up exactly till 15 volt. It will charge up to a value lesser than 15 volt because of loss through the resistor. There will be drop through the diode and drop through the device and all. Okay, fine. So now the question is, what should be the rating of this VD boot, right? What should be the rating of this VD boot? So can you tell what should be the rating of VD boot? Is the question
Should
understood?
be
Uh, it should be. Tell, no worries. Even if it is wrong, no worries. Just connect the cathode and
S1
connect the.
S1.
Yeah. So the point is, you started from here, right? Let's say we take the cathode, right? So the cathode, let's take it to the power side, okay? You end up over here, okay? And let's take the anode side. Anode side goes like this, and you end up over here, which is the ground. Okay. So now can you tell what will be the rating? VKA, cathode to anode rating. See, the cathode is, okay, so let's write cathode. Okay, so let's write what is the bootstrap diode voltage. So what will be VKA, right, or VD, right? What will be VK or VD? On the cathode side, you are having VC boot, right? VC boot is somewhere around 15 volts only, right? And then you are having switching node, okay, on the cathode side. And on the anode side, you are having some I into R boot, I into R boot, and then VDD. Is this understood? Is this fine? Just I am rearranging this particular equation. If you see, this particular equation is only coming over here. Is this fine? The voltage across the diode. VC boot plus switching node minus IR plus VDD on the cathode side and anode side.
Yes, sir.
Okay. So now you see that VC boot is almost 15 volt and VDD is also 15 volt. Almost, right? Almost same. So I will cancel out VC boot and VDD, right? VC boot minus VDD. So what you are left with is V switching node minus IR. So your switching node can vary between VDC and 0. So for the worst case rating, we will take VDC and IR is very small. So what you understand is your VD should be rated to your DC bus voltage. Okay. This should be rated to the DC bus voltage, your VDC voltage. Right? If your VDC is 800 volt, your diode should be rated to 800 volt. That is the one point. Okay. That is the drawback. Okay, so we were telling that we do not need multiple gate drive supplies, we do not need isolation and all, right? But one drawback is that the diode that you use should be rated to the DC bus voltage and that can increase the costs. Okay, but comparatively, people have seen that this is much cheaper than conventional whatever we had seen earlier. Do you understand why it is VDC? Why the diode is rated to VDC? Just apply KVL, you will see that it should be rated to the switching node, and you know that switching node voltage goes till VDC, right? So your diode should be rated to the DC bus voltage. Do you understand this? We have seen how to design the circuit.
Yes,
Sorry.
yes, sir.
Yeah. So in conclusion, what all have we seen? We have seen how to. Okay. So I will just conclude over here, and we can wrap up for the day. Okay. I think it is almost time also. So where did we start? I don't know where it ran off somehow. Yeah, so we started off over here, right? Conventionally, you have the microcontroller, and then you need to have two isolators for the top side and bottom side, and then you need to have two gate driver supplies, that is VDD and VE for the top side, VDD and VE for the bottom side. So you have two gate driver ICs, two isolators, and one microcontroller, and you of course have two VDD and VE for the top and one VDD and VE for the bottom. So this makes things expensive, right? So that is the motivation for Bootstrap. Can I use a single VDD from which I can drive both S1 and S2, complementary switching, right? Can I use a single VDD? So that is when we started off with this particular circuit, right? That is, first we saw how S2 turns on. So for S2 to turn on, I will turn on Q3, VDD, Q3, RG2, S2, and then back. And for S2 to turn off, we saw that the simplest path is to discharge through Q4, right? It will discharge through Q4. This is very simple as far as S2 is concerned. And for S1, for the topside device, we saw that there is a bootstrap capacitance, right? So what we will do is when S1 is turned off, right? That is when S2 is turned on, we also have a path for the capacitance to charge up, right? So the charging path for the capacitance was from VDD, we started going like this. It will go through C boot and it will flow through the channel of S2 and back to VDD, right? This is the charging path for C boot. And we saw that in order to limit the current, we added R boot. This is a current limiting resistor, right? And in order to prevent backflow of current, we don't want C boot feeding VDD. We want to see C boot to feed only like this, right? So in order to do that, we were having a diode deboot, right? This is something we added as we went through the circuit. Okay. So yeah, C boot charges through the channel of S2. That is true. Okay. Fine. And then how will S1 operate? So for S1 to turn on, it will go from C boot through RG1 and then back as indicated in green. And for S1 to turn off, it will be through Q2, right? That is CGS1, RG1, Q2 and back. Okay. This is just the general operation. So then as far as design is concerned, we saw that, okay, so C boot is just a capacitance. Obviously, capacitance will discharge, right? So what is the discharge? What is the delta V? So if let's say you are at 15 volt, we saw that capacitance will slowly discharge. So we want it to discharge not too much. We want to discharge only very minimally. Okay. So like that only we will size the capacitance, right? So we will know what is the delta V. This is the design parameter. I will fix that delta V should not be more than 2 volt. Delta V should not be more than 1 volt, like that. Okay. Once that is known, from the device data sheet, I will know what is QG. So with these two information, I will design C boot as what? QG divided by delta V, right? Simple expression. Okay. That is what we did, right? C boot is QG by delta V. Based on what is the delta V, how much you want it to discharge, and what is the QG, right? Based on that, you will design what is C boot. This is one design parameter, and the next design parameter was how to design this R boot. I mean, how to design the D boot, the bootstrap diode. So the rating for bootstrap diode should be the voltage rating. We just wrote the KVL equation, right? This is just from KVL equation, and we kind of saw that the bootstrap diode should be rated to the DC bus voltage, right? If your DC bus voltage is 400 volt, your diode should be rated for more than that, right? If your DC bus voltage is 800 volt, people use 1.2 kV diodes, okay, very high voltage rated diodes. So that is the drawback of bootstrap bootstrap circuit. But one thing you are able to see is you are able to achieve complementary switching of S1 and S2 with only one VDD. You need not have separate VDD for top device. Okay, with only one VDD, you are able to drive. So, any doubt so far in bootstrap circuit?
Sir, I have one doubt, not in the
Yeah,
circuit. What happened if any of the switch S1 or S2 failed to operate? Means any short circuit occurs or a device is not working properly. Means what happened to the circuit? What happened to the elements? Means connected to it.
what happens to these bootstrap elements, or you are asking in general?
I'm asking if the device gets failure. S1, for example, S1.
So S1 fails means, see, there are only two options if it fails, right? So one is mostly it will be short, right? S1 is gone. So that means that there is a direct path from VDC, right? S1 is shorted. So S1 is shorted means, let's say, so your question is S1 is short, S2 is, let's say, a proper device.
Yes.
Okay, that is your question, right? So at some point I will try to turn on S2. So then there will be a short circuit across VDC. That's your concern, right?
Yes, sir. If an
Right.
S1 get fails, automatically
Huh. Huh.
it will
Damage S2
make fail.
also.
Yeah, yeah, S2 also. The total circuit will get failure.
Correct. So for that only, do you remember in the around 4 5 weeks back we were seeing about this DSAT protection, right?
Yes, 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 yes,
So that
yes,
is
yes, sir.
what will happen. So what will happen is S1 is gone. So S2 will try to turn on. When S2 turns on, what will happen? There will be a direct short circuit. Okay. So because of direct short circuit, the current will rise exponentially, right? Current will rise. So because current, I don't know whether it is here or not. Okay. So because current is, it is there. So because current is rising, then what will happen? This circuit will come into play. We saw the how the circuit operates, right? The current will rise, so the voltage across the bottom device will go on increasing. We will compare it with a comparator, and then we will turn off the gate pulses for Q2 for the device S2. So that is how we save the device. Do you understand?
Yes,
This
sure.
DSAT protection will come into play. Do you
Practically,
remember?
this protection scheme is used. They are using this
Yes,
protection scheme.
yes. We have seen multiple times in our lab that DSAT for one device will trigger. Okay. If the DSAT protection triggers, so what, while implementing practically, how do you know that DSAT has triggered, right? So for implementing it practically, what we will do is after this comparator, I don't know whether you remember the circuit, but hope you remember the circuit. Okay. So after this comparator, we will be having, let's say we will have an LED. Okay. So, hmm, so the symbol is something like this, I think. Okay. So you'll be having an LED. If this LED turns on, right? If the LED glows, it means that the DSAT circuit has operated. Okay. Once the DSAT operates, because it is going to the gate driver turns off and the device is protected. So after this LED, now this LED will remain on. So once LED turns on, we know that okay, there is some problem. Do you understand?
Yes, sir. Yes.
Okay, we have seen multiple times in the lab that DSAT will trigger. If DSAT triggers, it means there is a problem. And we have even seen that, okay, DSAT has probably, let's say it has false triggered, just like that LED turned on. Let's run the circuit again. Again, we will run the circuit. Again, the DSAT LED will glow. That time we know that definitely some device has gone bad. So that is why this DSAT is triggering again and again. Do you understand?
That's how you come to know that the device get failure.
So this is one of the ways. Okay. The other way is that obviously you take a simplest way is you take a multimeter. Okay. You take a multimeter, put it in resistance mode and measure across the device. Okay. The resistance. So ideally when the device is in off state, the resistance should be in mega ohms, right? That is the device is off. So resistance will be in mega ohms. The multimeter will show OL overload. If the multimeter shows a direct short, right? That is, if you check in continuity mode, it will show a beep sound. So if
So,
it shows like that, it means the device is gone.
okay.
Okay. Or let's say there is some problem with your gate pulse itself, or let's say that both the devices are fine. Okay. Let's say both the devices are fine, both S1 and S2 are fine, but there is some problem with the gate pulse. That is, let's say the gate pulse for S1 and S2 are overlapping. Okay. If there is an overlap for S1 and S2, then also there is a problem, right? Even if the devices are good, if there is an overlap of S1 and S2, again there is a short circuit. In that case, you will see that the DSAT for S1 and DSAT for S2, both of them will trigger. Both the LEDs will glow. You will know there is a problem. So the point is that DSAT is a very good indicator. Okay, it has prevented a lot of devices from getting blown up. It will show you that okay, you're doing this mistake with your circuit. So yeah, so that's the point. The DSAT will trigger.
Okay, sir.
Okay, so any other doubt or is this fine?
Yes, sir, it's fine.
Okay, so I hope you understood DSAT. Okay, I will upload the slides. You can go through it, but it's very simple. Okay, I think seeing the circuit itself, you can easily understand how it operates. Okay, so yeah, just that you need to size C boot properly based on the gate charge and create your D boot accordingly. So if you go to commercial gate drivers, okay, commercially bootstrap gate drivers are available. Okay, in some bootstrap gate drivers, you have to attach the D boot and R boot externally. And in some, I mean, you have to attach the D boot and C boot externally. And in some gate drivers, the D boot will be built in. Okay, if the D boot is built in, they will tell that this gate driver is rated for 200 volt. it means that the bootstrap capacitor inside it is rated for 200 volt. Okay, you can search for commercial bootstrap gate drivers. Okay, there are a lot of bootstrap gate drivers in the market. They will tell that it is rated for 300 volt. It is rated for 600 volt. It means that the diode inside it is rated for 600 volt. Okay. And in some gate drivers, they tell that you can add the deboot externally. So according to your requirement, you can buy deboot rated for like whatever DC voltage and attach it. Is it fine?
Yes, sir.
Okay. So yeah, thanks for attending. We will close for the day. Okay.
Sir. Okay, sir. Thank you, sir.
Okay. Yeah. Good night.
Good night, sir.